Thank you very much. Please feel free to ask questions at any time. What I will be talking about is joint work with Marcos Epikropou, a student who just graduated this year. If you look at the title, I am absolutely certain that all of you know what linear programming is, but perhaps profit inequalities may be unfamiliar to you. So I'm going to begin by telling you about those. Okay. And specifically, profit inequalities are inequalities that are related to stopping problems. And so let me start with a very simple stopping problem, and this is the one that I'm going to focus on. I want you to imagine a sequence of boxes. In each box is a random number, and you know the distribution over the random number. And the distribution need not be the same for every box, so different boxes can have different distributions. Okay. You are going to open the boxes in a particular order that is given to you. So you go to box 1, you open it, you reach in, you pull out a number. That number is your reward. You can decide to keep that reward, in which case you are not allowed to open any of the remaining boxes. You can choose to discard the reward, in which case you can move on to the second box, open it, and select whatever is the random number in that box. Okay. There are a finite number of boxes, so at some point you have to stop. The only issue really is whether you want to stop at box number 1, 2, 3, or 4, given the reward that you've observed. And what is your objective? Your objective is to maximize your expected reward.
Genau. Wunderbar. Hallo? Hallo? Ja, ich höre dich noch. Wunderbar.
Does that make sense? Okay. So in this example here on the slide, you might have opened box number 1. You saw a reward R1. You found that unsatisfying, so you decided to go to box number 2. You open box number 2, you see the reward R subscript 2. You find that unsatisfying, so you go to box number 3. You open that, and you see a reward of R subscript 3. And perhaps you decide that's good enough, and you stop, in which case you walk away with the reward R subscript 3. Okay. Any questions? Okay. So how do you solve this problem? It's not hard to see that you can always solve it by dynamic programming. What do you do? At any box that you're currently at, you look at the reward that you have seen, you compare that with the continuation value. If the continuation value exceeds the current reward, you continue. If not, you stop. Okay. So in terms of solving this problem, nothing terribly deep here. Okay. Now, what was interesting was that in 1978, Krengel and Suchestin made the following observation. Skip the dynamic program. Perhaps do something simpler. Okay. There is a simpler strategy which has the following property. It will deliver an expected payoff, which I'm denoting by opt subscript ON in the slide. So think of that as, no, I'm sorry, let me take that back. Start again. What Krengel and Suchestin observed was that there was a relationship between the expected payoff from this dynamic programming algorithm and the expected payoff from the following variant of the problem. And the variant of the problem is this. Supposing I allow you to open all the boxes simultaneously and pick the best reward that you see. They call this the offline problem. So you see all the rewards and you get to pick your best reward. Their interpretation of the offline problem was that there was a prophet capable of seeing the future The profit effectively would know all of the rewards and pick the best reward. And their result was the expected payoff of the dynamic program, which I'm denoting opt subscript ON to mean optimal payoff from the online problem, is at least 1/2 of OPT subscript OFF, optimal solution of the offline problem. So in other words, you, with only probabilistic information about the future rewards, can generate an expected payoff that is at least 1/2 of the expected payoff of the prophet who has full knowledge of all rewards. And this was an example of a profit inequality. What was remarkable about this was that the expected payoff of the online strategy was within a constant factor of the offline strategy, something that one would not have expected, perhaps, necessarily. Okay? In 1984, Esther Samuel Khan pointed out that this inequality held even if you didn't use the optimal dynamic program. She proposed a simple strategy which involved a single number, and the algorithm was this: whenever you see a reward that exceeds that number, stop. And she proved that following that simple strategy would generate an expected payoff that is at least 1/2 of the optimal offline strategy. So these are the classic results on profit inequalities from the beginning of time. These two papers have generated a flood of other work, most of it actually in the last 10 years, devoted to either strengthening the bound of 1/2 or considering variations of this basic stopping problem. So what are the variations that people have looked at? Well, if the rewards were IID, could you do better than 1/2? If you could choose the order in which to inspect the boxes, could you do better than 1/2? On the other side, people have asked, well, perhaps there are generalizations of this. Why do I have to pick one box? What if I'm allowed to pick K boxes? Okay. What if the boxes have weights and I'm only allowed to pick a subset of boxes whose combined weight does not exceed some constraint? In other words, there's a knapsack constraint in the background. Once you go down that road, then you find yourself saying, why knapsack? Why not matroidal? Perhaps each box represents the element of an independent system, and I'm free to choose any subset of boxes that forms an independent set in this independent system. Any questions? Okay, now, these profit inequalities that have been obtained are typically obtained using case-specific arguments that are sometimes quite involved. What I want to talk about this morning is an approach to deriving profit inequalities using linear programming methods. And I'm going to illustrate with the standard stopping problem that I began with. So you must inspect the boxes in a given order, and you are only allowed to pick one box. So let me first write down a non-linear program that gives us the solution, the optimal solution to the stopping problem. So here it is. The relevant decision variable is right here, and I'm underlining it in blue. This is the probability of choosing box I, stopping at box I, given that you observe a reward of Ri and that you have not stopped before. So Qi of Ri is a conditional probability. So conditioned on not having stopped before box I and seeing reward Ri, Qi of Ri is the probability with which you stop at box I. Okay? So I am allowing you in principle to follow a randomized strategy. You do not have to deterministically stop at a box. Now, with those variables, in the bottom half of the slide, I have written down a nonlinear program that solves the stopping problem. What is the objective function in the nonlinear program? Well, to begin with, at each box I am looking at the expectation over the history of rewards that I see up to and including box I. What am I taking an expectation of? Well, notice the first term that I'm marking with an arrow. That's the reward that I see in box I. That's the probability that I stop at box I, conditioned on me not having stopped before. And what am I multiplying it by? I'm multiplying it by the probability of the event that I never stopped before box I. And the reason I can multiply up these probabilities is because, remember, these are all conditional on not having stopped in the time period before. Okay. Any questions? Now, it's a nonlinear program. I said that I could solve the stopping problem as a linear program. So what I'm going to do is convert the nonlinear program into a linear program. And I'm going to do that by a change of variables. And that change of variables appears at the top of the slide. So here is the new variable, capital Qi of Ri. The interpretation of it is as follows. It's the expectation of choosing box I, stopping at box I, given that the realized reward is Ri. Notice there is no conditional statement here. It is the unconditional probability that you will stop in box I, given that you see reward Ri. In economics, this is sometimes called an interim allocation variable. And here is the definition of capital Qi. It is the conditional probability that you stop at box I, given that you see reward Ri, multiplied by the expectation of the event that you never stopped earlier. Okay. I claim that if you use these interim allocation variables, capital Qi, then in the second half of the slide is a linear program that describes the optimal stopping problem. What is the objective function? Well, I am maximizing. What am I maximizing? I am maximizing the expected value of the following at each box. It is the reward that I get from box I multiplied by the interim probability that I will stop at box I if I see reward Ri, the unconditional probability that I will stop at box I given that I see reward Ri. And then I'm adding that up over all boxes. Now, what's the constraint? Well, this is the unconditional probability that I stop at box I if I see reward Ri. What is this that I am boxing in blue? It is, roughly speaking, the expectation that I stopped at some earlier box. And I'm claiming that those two things have to add up to something that is at most 1. Okay. So you can think of that constraint in the following way, which is roughly speaking, the total probability that I must allocate across all boxes to stopping across all boxes cannot exceed 1. This is clearly a necessary condition for the capital QIs. It is not obvious that it is a sufficient condition. Okay? The key result is that this is not only necessary, but sufficient. Okay? If you believe that, then what you see before you is an exact linear programming description of the stopping problem. Okay? The size of the description is polynomial, basically in the number of distinct rewards that you can achieve and the number of boxes. Now, why is this interesting to observe? The reason this is interesting to observe is because if you go back to the original non-linear programming formulation, the number of variables that you have is exponential in the number of distinct rewards, because you have one variable for every sequence of rewards that you could observe. Any questions? Okay. Now, what's the proof that this is an exact linear programming description of the stopping problem? Well, it boils down to the following piece of algebra. Recall, capital QI was defined in terms of QI multiplied by what you currently see in the denominator. So what I've simply done is rearrange things and taken something that was multiplying little qi and put it in the denominator under capital QI. There is then an induction argument to show that what you see in the denominator is exactly the same as what you see in the denominator in the second line of the slide. Okay. Now, it is not hard to see, but one has to think a little carefully about the notation. So let me tell you what the notation is. Over here, I have got the probability that you did not stop at box 1, 2, 3 up to I minus 1. Given that you saw rewards T1, T2, T3 up to Ti minus 1. What is this? This is the probability of the event that you see that sequence of rewards. Okay. So what I'm simply adding up is the sum over all possible profiles of rewards of the probability that you never stopped. Now, if you look at these things, okay, you have to think about the definition of capital QI. Let me remind you what it is. Capital QI is the little q's multiplied by the expectation of the event that you never stopped earlier. That means if I look at each of these things, these are the expectations of the event that you never stopped earlier, which means that I can rewrite them involving the capital Q. And that's the basis of the induction argument. Okay. Now, if you accept the algebra, notice capital QI is equal to, little qi is equal to capital QI divided by this linear combination of capital Q's. The only constraint on the little QIs were that they were between 0 and 1. So I can eliminate the little QIs and simply require what I am boxing in red now to be between 0 and 1, multiply through by the denominator, and it gives you this, that I'm boxing in red. And that's the argument for why this is an exact linear programming description of the stopping problem. Now you will notice I have summations there. That's because I implicitly assumed that the random variables in the box were discrete, so they could only take on a discrete number of values. If you insist on the random variables being continuous, you can use the same argument. The summations that you see there are replaced by integrals. Any questions so far? Okay, now what can we do with this linear programming formulation? Let me show you one thing you can do by rederiving the classic profit inequality result of Krengal and Suchestin. Consider now the offline problem where you see the reward in every box. And therefore you can pick the biggest reward. I am going to denote by Q star the expectation, the following object. Q star I of Ri is the probability that you select box I when it has reward Ri in the offline problem. So once again, it's an unconditional probability. What is that probability equal to? Well, I have n boxes. Each box gives me a number. I am going to pick the biggest number, which means I'm going to pick the highest order statistic. So Qi of Ri is simply the probability that box I has the highest order statistic when it gives you a reward of Ri. Okay. So I could work it out explicitly, but I don't need to. Here is what I'm going to do. I'm going to take this Q star, which is the optimal solution to the offline problem. I am going to divide it by 2. And I claim that this object that I divided by 2 is a feasible solution to the following linear program. So let me say that again. I am going to take the optimal solution to the offline problem, which is given in terms of Q star. I'm going to divide that by 2. I claim that that object, which I'm pointing to now with the arrow, is a feasible solution to the linear program that I described earlier. That means I am taking the optimal solution to the offline problem, scaling it by a factor of 1/2, and claiming that that corresponds to an optimal solution to the online problem, without explicitly constructing an online solution. Everyone with me so far? Okay. Now, let me just prove to you that it is indeed a feasible solution to the linear program that I mentioned before. Well, what was the constraint to the linear program? Let me remind you. It was this. I am replacing each qi by a half q star. Well, what do I know about q star? Q star I of Ri is the unconditional probability that I select box I when it displays reward Ri in the offline problem. It's a probability, which means it's less than 1. So therefore, this object that I am now circling in blue must be less than or equal to a half. Now, what is this object here that I am boxing in blue? This is basically the sum of all of the probabilities of having picked from box 1, box 2, up to box I minus 1. Well, the sum of those probabilities cannot exceed 1 because I can only pick one box. So therefore, the term that I have boxed in blue must also be less than a half, and therefore the sum must be less than or equal to 1. I have shown you feasibility. So I have exhibited a feasible solution to the linear program. What is the objective function value of this feasible solution? That appears in the line just above the constraint line. The expected value of this feasible solution is, by construction, half the expected value of the optimal offline solution. Okay. What I think is interesting here is that we are using the optimal offline solution to guide the construction of an online solution that is within a constant factor of the optimal offline. So what is interesting about this linear programming approach is that it allows you to take information about the optimal offline problem and use it to say something interesting about the online problem. Any questions so far? Okay. So what else can we do with this trick? Well, here's another one, which I will just state. Okay. What if the boxes are IID? So you have the same distribution in every box. Can you get a stronger result? The answer is yes, you can. What's the basic idea? The basic idea is to take, once again, what you know about the optimal offline solution and use it to construct an online solution. Instead of scaling, because we're going to try and get a better bound than 1/2, we're actually going to use the online solution to determine an order so not an order. Notice capital QI. This is my conjectured solution to the offline problem. It depends on the offline solution. Okay. Roughly speaking, what am I doing? I am trying to mimic the offline solution, because what is this term over here that I'm circling in blue? It represents something like a probability of not having stopped at boxes 1 up to I minus 1. So basically, I am using the unconditional probabilities from the offline problem as my probabilities for deciding when to stop in the online problem. Okay? If you do that, and a simple piece of algebra that I won't repeat, because it's really just 2 lines, you get a bound of 1 minus 1 over e. In other words, if you follow this online solution, it generates an expected payoff that is within a fact where it is at least 2/3 of the optimal offline. Now notice, I do not explicitly construct the online strategy. Everything is in terms of these interim variables, these unconditional probabilities. Now you may ask, surely we care about the offline strategy. How would you construct it? Well, the answer is you could construct it by reverse engineering the formulation, which is once you have the capital Q's, you can plug them into what I just boxed in blue, and out pops the conditional probabilities of stopping. So I can always recover the online strategy from the capital Q's. Here's another example of a result that you can get, which is, what if you can choose the order in which you can examine the boxes? So you don't have to look at box 1 first. Well, once again, we use information about the optimal offline solution, and we use it to construct an index, which should look something like the greedy index you see in knapsack. And we examine the boxes by decreasing value of that index. And so this tells you the order in which you examine the boxes. And in terms of whether you should stop or not, you mimic the offline unconditional probabilities. And the algebra, again, is fairly simple. I won't go through it, but you get a bound of 1 minus 1 over e. So if you can choose the order of the boxes don't have to be IID. You can do better than 1/2. Okay, is there a more general problem that we can tackle? Well, I will write down a general problem that we believe we can tackle, but we haven't succeeded yet. I will then describe a problem that is less general, but more general than the previous ones that I told you, for which the technique gives us the desired result. So here is the more general problem, and let me describe it not in terms of boxes, but in a way that I hope is more natural. I want you to think of each box as an agent. So there is a sequence of agents that are arriving one at a time, asking for some service. And the reward of servicing an agent is not known in advance. You only know the reward from servicing them when they show up. And the reward from servicing agent I is a random number, and let's say it turns out to be Ri. The level of service that you give an agent is some real number, and it can depend on the history of rewards that you have seen so far. What is the constraint? This service that you're offering the agent may consume multiple resources, and so we're going to model that as a collection of linear inequalities. In the original stopping problem, there is one linear inequality, which is simply the sum of the service levels cannot exceed 1. Okay? Here we're allowing for more than that. Okay? So you could imagine a situation where an agent arrives, their request for service may use different resources at different rates. And those rates would be encoded in the matrix A. Notice the subscript I on the matrix AI. Well, because the columns in your constraint matrix grow with the length, with the number of boxes or agents that you've seen. So every agent introduces a new column to your linear program. So what I've just described then is at least one version of what you might think of as an online linear programming problem, where the columns arrive one at a time. The constraints in the column are known, but the objective coefficient associated with a column is a random number that is not known until it arrives. Any questions? The idea that we have is the same, which is we define these unconditional probabilities. And the goal is to show that if you take an optimal solution to the offline problem, so the offline problem is the one where you see all the columns of your linear program and then solve the linear program. Okay? We want to take that, divide that solution by 2, and show that that's a feasible solution to the online problem, and that immediately gives you a profit inequality of 1/2. Okay? If what I said works, then this would give us a result that contains all previous profit inequality results for matroids, for polymatroids, for knapsack, and so on and so forth, all as a special case. But as I said, we've not yet succeeded on that. We have succeeded on one simple case, the knapsack problem. So the A matrix just has a single row. Let me close with a concrete application, because one of the unfortunate aspects of this profit inequality literature is it has completely divorced itself from any kind of reality. People are driven essentially by the mathematical appeal, and it's a race to, can I generalize the previous, can I generalize what everyone else has done by adding more constraints, by adding correlation. So what I'm describing now is the first genuine example that I'm aware of why we might care about these kinds of stopping problems. Okay? And it is motivated by something called computational sprinting. So some of you who know perhaps more than I do about hardware in computers know that the chips, if you try to speed up the processing of a chip, that increases the heat that is generated and subsequently damages the chip. Okay? And so that's a physical constraint on how much processing per unit of time a chip can do. Now, it turns out that you can actually exceed the thermal limit on a chip for short periods of time. And so this raises the possibility of what is known as computational sprinting, which is for brief periods in your computation, I will push the chip above its thermal limit. Okay? I can do that for a brief period of time, but then I have to bring it down below its thermal limit to allow it to cool down. Okay? Now, there is a constraint that links all these pushes above the thermal limit, an aggregate constraint, which says in aggregate over some time period, there is a limit to how much I can do this. Okay? Now, so they do this in many large-scale in many cloud servers, right? But the issue they face is that the benefit to sprinting is not known ahead of time. It is only, in other words, the computational speed up that you will get from sprinting is only known at the time that you initiate the sprint. Okay? There are some machine learning algorithms that will forecast the benefit from speed up at any instant in time. So those give you a probability distribution of the potential benefits at time 1, time 2, time 3 from speeding up. Right? And the computational limit is a single knapsack constraint. And so you have here an obvious stopping problem with a knapsack constraint, which has to be solved quickly. So you cannot afford to do the dynamic program. And so what we're proposing is our online strategy that we get from the linear program to do these computational sprints. Right? Now, unfortunately, the actual computational sprinting problem is a little more difficult. There are actually other constraints beyond the thermal power constraints that you have to worry about, which is why we are very interested in being able to solve the general linear programming version of the stopping problem. Now, I think I've taken up more of your time than I should have. So let me stop here and thank you for your attention.
Thank you. Very good. All right. Any questions? No, thank you, Markus, for the nice talk. Any questions?
Or maybe I have one question.
Go ahead, please.
I take from what you explained that the RIs are always independent. They may not be identically distributed, but they're always independent. Is that correct?
Correct. Across boxes.
Across boxes, exactly.
Yes. So you put your finger on the weakness of this approach. In other words,
I didn't mean to do that.
That's perfectly correct. It's perfectly all right. This linear programming approach breaks down the moment you introduce correlation. And the reason that happens is because we're making use of the fact that we can work with these unconditional probabilities, which allows us to say that the objective function is linear in the capital Q's. That's what, okay. Now, unfortunately, if you allow correlation, you can still define the capital Q's. That's not a problem. The objective function is no longer linear in the capital Q's.
Yeah, right.
Now, to my mind, this says, okay, linear programming isn't going to work. It doesn't rule out the possibility of using convex programs. Right? So, because you can certainly write the problem down as a nonlinear program. Not interesting. Anything can be written as a nonlinear program. Right? But between nonlinear and linear, we have things that are still useful, and convex is what comes to mind. Now, can any instance of a stopping problem with correlation be written as a convex program? I suspect not. So you might have to impose some structure on the dependence relations, and then you could get a convex program. Right? Now, where that would be, the most obvious place where that would be useful is in evaluating the value of an option, because many options are basically stopping problems. What makes them hard is the correlation and the rewards across time. Right? So if you could, but in those settings, there is some obvious structure on the correlation, which I think could be milked to advantage to generate convex relaxations and then prove corresponding profit inequalities for those problems.
Thanks.
Good. Any more questions? I had a place where I couldn't follow. You mentioned one of the formulations were exponential and the other wasn't. If I look at the QIs, it seems like both kinds are indexed by the same structure. So I missed there.
Okay. Hold on one second. So
Slide 8 or something like that, maybe.
Now, here we'll do. So notice in the online problem, I have to specify the probability with which you will stop at box I as a function of the sequence of rewards that you've seen.
Yeah.
Right. So that makes an explicit linear programming description or an explicit mathematical programming formulation of the stopping problem exponential in sort of any natural measure of the size of the input, right? But what we are what we have exploited is if you move to the unconditional, you get a polynomial, at least for the case of one box, you get a polynomially sized description of the stopping problem. Okay? Now, if you are allowed to pick 2 boxes, we can show you that there is no polynomially sized description using these capital Q variables. The size of the formulation then grows exponentially. So the case of 1 box in some ways is very special. Okay? So once you go beyond 1 box, let me back up a bit. At the end of the day, what are we doing? We're basically taking, if you think about it, we have a linear program. There's some linear program in the little q's. What we're doing is we're projecting down to a lower dimensional subspace. So, it's lower dimensional, we should expect to see a blow up in the number of constraints. Okay? For the case of 1 box, no blow up. For the case of 2 boxes, blow up, right? So you're not going to be able to use this method to get nice linear programming descriptions of more general stopping problems. But we don't need an explicit description of the linear programs. Right? What we're doing basically is we're saying we don't have an explicit description, but we can still prove that if you scale the offline problem by 2, it's a feasible solution to the online problem.
Okay, thank you. All right. Any more questions?
Maybe I have another one.
Go ahead, Ray.
This might be a much more stupid question. If I understand correctly, the strategies you obtain are randomized strategies. Right? This is the conditional probability of stopping, given that you see what you see, but you still, to implement it, you would still toss a coin.
You would still toss a coin, yes. So
can you project it down to something non-randomized, to a pure strategy?
Okay, very good. So if I go back to the basic stopping problem where there's just 1 box. Here's the nonlinear program, right? If you look at the nonlinear program, even though I allowed you to have a randomized strategy, if you look at this nonlinear program, you can easily conclude that the optimal solution must have the little qi's being 0 or 1. Why? Because in the objective function, basically fix the qj's from the boxes before, then it's linear in qi. And so you would either set qi to 1 or to 0. Okay? So therefore, even though I allow you a mixed strategy, in the optimal solution, the optimal solution will be deterministic. Okay, now, so this is true for 1 box. Now you may wonder, and that is exactly what you're wondering about, is there in other words, is the assumption of a randomized strategy, are randomized strategies richer than deterministic? And the answer is, in some cases, yes. However, we have the following conjecture, and we prove some special cases. If your linear programming polytope is integral, in other words, the more general problem here, where is it? If this is an integral polytope, okay, then we claim that the optimal online solution will be deterministic. So in other words, even if I allow you to randomize, there is an optimal solution in which you will choose the boxes deterministically.
Mm-hmm.
Okay. Now, if you insist that you want a deterministic solution, then we would have to add constraints that say solve this as an integer program. Okay. And then the answer is we don't know how to do that.
Right, thanks.
Good. Very good. I have more last questions. Yeah.
But wouldn't in the general case, the second inequality that we see on this slide below the boxed blue one more or less always destroy the integrality of the polytope?
This is what you might think, but yeah, as I said, for some special cases, it apparently doesn't, which is why we conjecture.
Okay.
Actually, I should be more careful. The conjecture is not integral. The conjecture is if this guy is totally unimodular, then the optimal solution to the stopping problem will be integral. Sorry, I shouldn't have said if the polytope is, it should be if it's totally unimodular. And the one box case is clearly an example. The other case that you might think about is polymatroid. Not quite totally unimodular, but right, all of the basis matrices are totally unimodular.
Okay. Any more questions? No. Gained a lot of insight. Great. Very good. Thank you, Rakesh, for the very nice talk once again.
Not at all. Thank you all very much. And I think you said this chat afterwards, or is that the end?
Beg your pardon?
Yeah.
We plan to have a chat before it.
Oh, okay. That's right. Okay. My apologies for that. As I said, I had trouble.
Yeah, but we have plenty of opportunity for questions. So thank you. I think that would be the time to end it.
Yeah, and thank you, Sven.
Good. Goodbye. Oops.
Bye.